Hey there, everybody. This is Zach Brumbach. I'm TAs for Math 1553 at Georgia Tech. I got this question from the second question of the last worksheet, which was about March 3rd, I think. Time I review to go over it, so I'm just going to go over it here. It's okay. So what the problem supplies us with is it says A is an M matrix and B is M. I've drawn those off here to the side. It's just the general shape of the two. Okay. And what I have written below it is when you multiply A times B, it gives us an M by M matrix. And the way we can tell this is when we multiply two things together, I like to write their dimensions under them. And I draw a box around their middle things. If they're the same, I draw a check, and that means we can multiply them. And then whatever's on the outside of this box, in this case is M and M, that is what our product is going to be. Okay. So let's back on the first statement of what they tell us about this question. Okay. And now X is in Rm, and let AB times X be the thing we're talking about. Where must this lie? Okay, well, ABX, okay, is just the same as the column space of AB, okay, because this is just equal to some B vector, right? And those B's comprise our column space, right? So from here, the way I like to think of this question is I like to think of it as A times BX, okay? Where B is a matrix and X is a vector, right? So A is, this is unnecessary, right? Of A, B, and X, okay, times X. I'm gonna get an N by one vector, okay? And what this is this is essentially if I'm just transforming X by B only, okay? So let's call this new vector A times V, okay? So this is just saying B times X gives me some transformed vector V, right? Say V is transformed X, okay? So as we can see here, this is just me rewriting the original question. And from here, one can tell that this is just in a column space of A itself, okay? So column space of A and B must always be contained within the column space of A. In fact, over here, I'm gonna write this nice little note. The column space of A, B must always be a smaller than, or rather a subspace of in this context, of column space of A. Okay, and we can translate this into numbers by saying the dimension of the column space of AB must always be less than or equal to the dimension of the column space of A. Okay, so we can also rewrite this as rank of AB is always less than or equal to rank of A. Okay, and the whole reasoning behind this is if you do B first and then A is the last thing that you do, so that's essentially where you end up, okay? Think of if B is just a reflection and A is us moving from R2 to R4, we're always gonna end up in R4, okay? That's the most important thing, is the last thing that we do, okay? And just as a little note on that, just for clarity, when we do different transformations times X, we always work inside out in order, okay? So this is first, second, and third. And notice how they multiply from X going out, okay? All right. So these equations are going to be important. I'm going to talk about them in the following part as well. All right. So part B says let if M is greater than N. So before I even do anything, I'm going to rewrite this. I'm going to rewrite A and B in maybe a form I can see them a little better. A is a tall M by N, and B is a wide N by M. Okay, so that's just so I can see the shape of both of these. Okay, so from here, Okay, columns of A, B could be linearly independent or dependent. Independent columns means you have a pivot in each column. Having one and having multiple are the same thing, okay? So looking at this, the way we can kind of work our way through this is we think of the most limiting factor. And like we talked about in the last part, A is the last thing we do here because it's A times B, okay? Times X, and we work out, okay? So A is our most limiting factor here, all right? And if we look at A being tall, M by N, okay? How many pivots can they have at most? Well, it's most limited by this N because it's tall and skinny like that. So it can have at most N pivots. Okay, and this is at most, best case scenario, okay? So from here, I'm going to use one of the facts that we derived from this first part, and that's just the rank of A must always be greater than equal to the rank of AB, okay? So the rank of A is N in this case, it must always be greater than equal to rank of AB, all right? And let's recall that AB is M by N by an N by M. Check, and that results in M by M, okay? I'm just gonna write this over here. M, M, A, B. So this can have at most M pivots from just geometry. We don't know this for sure, but I'm just saying the shape of it can generally have that, okay? That's not an answer to our question. It's just kind of an observation of the shape of it, okay? All right. So, like you said, the rank of A must always be greater than the rank of AB because A is the last thing that we do. So whatever we do before that can only limit it more, okay? Think of it as you start B with 5 pivots. Okay, so it's some sort of like R5, if you will. And A has 3 pivots, R3, okay? As we change from B to A, we have to cram this R5 into R3, okay? So the resultant will be 3 pivots. So what will always happen is A is the most limiting factor. Okay, so it's over. Going back here, we know that M is greater than N, right? And so we know that the rank of AB is always less than or equal to M. It's always less than M. So we can cut out this middle piece and say M is always bigger than the rank of AB. Or if you'd like to read it in a way that's a little bit more straightforward and answers our question, the rank of AB must always be less than M, okay? And since it's M by M, like set up here, okay? If it's M by M, and we can have at most, did I write that backwards? Oh, I did write that backwards. I did. I apologize. Okay, so if we can have at most N pivots, okay? Ahead of myself for the next part. Okay, then we can never, ever, ever have up to M, okay? Yeah, I'm greater than N. What we're concerned with is this, right? So M must always be stricter than the rank of AB, okay? Strictly greater than, okay? So what that means is the rank of AB can never be equal to M. It must always be less. So we will always have one free variable in AB, okay? So I say one, but I mean at least one. Okay, and if we can always, if we must always have at least one free. These columns can only be dependent. They can never be independent, okay? Okay, so moving on to the next part. I've rewritten this part D just to make it a little more clear and following the trend of what we looked at in part C. So I changed it so that this would be AB to line up with what we had in the last part. And we had M greater than N in the last part, and now we have M less than N. So let's look at this now. So this means A is wide. It means B is tall. Okay, it's AB is still M by M. Okay, so the columns of AB. Let's rewrite rank of A always in greater than or equal to of AB. Okay, line up here. This is just where I like to draw things so we can see it the best we can. Rank of A can always be, or can be at most M. So we can replace this with M greater than equal to rank of AB. Okay. And if we see this, our rank of AB being can equal M now, means we can have a pivot. In each column. Okay, which means can be independent, or it could be dependent. We don't know that for sure. Okay, another way to write this would be we start with B, which we look at this, and we can have N pivots. Okay, and then we go to A, which has N pivots. So AB can have at most N pivots. Think of this as kind of like a funnel, okay, or something that's more limiting as we go down. All right. Say if B was N plus 1 and A was still N, we could still only have N pivots at most for AB, because A is our most limiting thing, okay? Always, always, always. This is really just what this whole question, this equation here, okay? So hopefully that makes sense. If it doesn't, you need to leave a comment, send me an email, post on Piazza. Any of those are totally fine. And now to go into the last question. M is greater than N, and A exclusion has non-trivial solutions. Well, if it has non-trivial solutions, that's the same as saying there exists a free variable. Okay. Or rather, not in each column. Okay. So having M greater than N, let's rewrite this again. M, N, tall A, wide B. AB is M by M. Okay. So actually, no. Okay. So BA, okay, it's going to be, come on, let me zoom. So B is N by M, A is M by N. Box these up. Hey, they can be multiplied. How surprising. N by N. So that means BA, N by N. Okay. This one talks about null space. All right. So something to kind of note for this one is one, we have switched orders, BA. All right. So it's going to be BAX. All right. And what we're looking for is the columns BA could be independent or dependent. This is the same thing. No free variables. And this is has free variables. Okay. So if b a times x, okay, is what we're looking at, and we know that there are non-trivial solutions, okay? If I pick any of those non-trivial solutions, okay, so say let v be in null of a, okay, or v is non-trivial solution to ax equals. So if my v is in here and we say that this has a trivial solution, so it has a dimension, so there is a free variable in a at least, okay? And again, now we're talking about null space, not column space, so we can't use those equations that we've talked about in the last couple parts. So if v is in the null space of a, then if I have b a v, I'm just going to put parentheses around it to kind of separate it out. If we know it's in the null space, we know that this is just b times the zero vector, right? Because v being in the null space means a times v is zero. That's the definition. No, it's always zero. Actually, reciprocal identity to the one we talked about is the null space. Question must always be greater than or equal to the null space of a. Okay. Then if you want to see it in a form that's maybe a little more consistent with the previous parts, which is also fine, we can just switch a and b. Okay. And what this means is as long as I have a null space for a, all right, it has to be smaller than my null space of b. Because as we can see here, this is the best way I can kind of show this, is as soon as we have something in the null space of a, okay, it goes to zero, okay? But alternatively, if v isn't in the null space, then we have b times some new vector, okay, I'll call it, I don't know, w, okay? Or av equals w, it's just some vector, right? Some non-zero vector isn't in the null space, okay? But w could still be in the null space of b, so this could still be equal to zero based on b's own null space, okay? So b can add to this null space. A is the most limiting factor, or the second thing is the most limiting thing for null space, okay? And up here we had the first thing, more limiting thing for column space, okay? So I can rewrite this one more time. It's dimension of null of AB is greater than equal to the dimension of the null BA greater than equal to dimension null A. Okay, which for this question in itself, all right, I'm just going to copy this to keep it separate than my identities. Okay, so for this question in particular, we knew this was greater than 0. Okay, so what I can do is I can say the dimension of the null of BA must be greater than 0, or if you'd like, if you prefer, greater than equal to 1. Okay, so this is me saying BA has at least one free variable. Okay, so thus, if it has at least one free variable, where did the actual question go? If it has at least one free variable, it can only be dependent. It cannot be independent. Okay. Cool. And this concludes my solution to problem 2.